Hello, this is John Lester Miller welcoming all to Science for the Board on a monthly schedule, the first Wednesday of the month at 6:30 Pacific. Next month, Corinne Foster will be giving her follow-on talk to Neanderthals. Her first talk on the Denisovans pulled over 2,800 views on YouTube. Oh, please mute your mics to keep the background noise low. Tonight's talk is Titan Through the Eyes of the DISR by the amazing Laura Ellen Wood, Dafoe. It is the second part of what she did a month ago, concentrating on the science. This talk concentrates on the science of Titan, including atmospheric physics, aerosol properties, atmospheric chemistry, and surface topology. Titan is a large, extremely interesting moon orbiting beautiful Saturn. The Cassini spacecraft went into orbit around Saturn and it dropped the Huygens probe onto this moon. This probe contained a DISR. This is the only piece of human hardware on a moon of another planet. It was a very successful mission, and I am sure much of its success is owed to by our speaker tonight. Laura Ellen Wood Dafoe has a BS in physics from the University of South Carolina, the wrong USC, and a master's in math from the University of Colorado. She is married to another aerospace photonics engineer and has 3 daughters. She lives in Colorado and did not lose her house in the recent fire. In the past, her car's license plate was Frolic, and her initials are LED. She started her career at Lockheed Martin in Denver in 1984, working on several electro-optical space programs. And I was fortunate enough to work with her on a couple classified ones. She also met Ed Friedman there. When Lockheed won the ESA contract for the DISR, Laura became the lead systems engineer at a very young age and was key to its development and success. Mrs. Dafoe left Lockheed Martin in 1995, but consulted part-time with the University of Arizona's Lunar and Planetary Laboratory, supporting the DRS mission. So she was there throughout the whole mission. She was involved until the last papers were published. She now telecommutes, and this is way before COVID. She started this, 8-9 years ago. She telecommutes with the Goddard Space Flight Center in Maryland, supporting 5 polar orbiting satellites. She is also the interface manager for a new science instrument that will measure the total Earth radiation. That is key to climate monitoring and forecasting climate change. Looking back in my career, I have had about 300 people report to me. 2 stand out, and interestingly, they are both women, and Laura is one of them. Take it away, Frolic.
Thank you, John. Thank you very much. And yes, a note about the telecommuting. I started telecommuting in 1996. That was before the World Wide Web was really up and running. So I think I probably was one of among the very first to start telecommuting and have telecommuted for a long time. Okay. So let me make sure I am. Can you confirm that I am sharing this in presentation mode now?
Yes.
Yes. Okay, great. Thank you. So as John said, I did work DISR. I worked it from 1991 till 2008. Papers still are being written, but the primary papers were done at that time. I was systems lead at Lockheed Martin and then became an analyst at the Lunar and Planetary Lab. So just one second here. Here we go. So a month ago, as John mentioned, I talked a lot about the instrument itself, the instrument development, what the Titan was like and why we wanted to go there. Tonight, we're going to talk about the Huygens mission as it actually occurred and just do a top level view of some of the key scientific discoveries. And I'm going to give the same disclaimer this time. I used to be an expert. I did work DISR full time for a lot of years and part-time for the latter ones. I've lost some of the details because I have moved on to polar orbiting weather satellites. So I've lost some of the details crisp in my mind, and some research has continued while I've moved on. It was actually kind of exciting. I went to the American Geophysical Union meeting a couple of years ago and was just browsing the papers, and there was my instrument, and there was a grad student there presenting a paper on DISR. It was pretty fun. I know a lot of the Europeans are continuing to do research on the data that we sent back. So, and some of those details I'm not up on, some of them I am. So I just want to have that disclaimer. I am not the world's expert on all things Titan, but I do know some things, and I'm glad to share them with you. So as a quick refresher, the Huygens mission was a probe. It descended through the atmosphere of Titan. Titan has an atmosphere very much like Earth's, predominantly nitrogen. Earth has a water cycle that defines its morphology and the atmospheric activity, and Titan has methane that operates as water on Titan. The probe went through the atmosphere spinning like a frisbee as it goes down under the parachute, and lasted about 2.5 hours before it hit Titan's surface. So the Huygens probe science objectives, as John alluded to, are mainly atmospheric objectives, figuring out what the solar heating rates are, forcing dynamics, what the thermal balance in the atmosphere is. Also these tholins, these are aerosol properties. They form a thick smog on Titan. It's what Voyager saw when it flew by, saw that orangish, hazy moon. These are these aerosol particles that Carl Sagan termed tholins. We want to know how the methane is resupplied from the surface of Titan into the atmosphere, and then of course the nature of the surface. I'm not going to talk about these next few charts. We did cover them last time, but I wanted just to refresh your memory. As the probe rotates, we're taking imagery from almost nadir till just above the horizon. The idea is to take a panorama all the way 360 degrees and do that as you descend through the atmosphere. We hope to see the surface from the top. Multiple images of the same area would allow us to use stereographic projection to determine altitudes. Then we'd use the ground track to measure winds. The down-looking spectra help us to measure some atmospheric chemistry looking down. And then near the surface science lamp would turn on. It's an incandescent lamp, black body radiation. It has a continuous spectra. So it fills in those methane absorption bands so that we get a clear spectral signature of the surface. That was one of the reasons that we won the proposal, was that surface science lamp, so that we could accommodate for those methane absorption bands, removing all of those wavelengths from the incident light on the surface, and really get a good spectral signature. The up-looking spectra, when we have the direct solar beam in our view, allow us to measure those methane absorption coefficients. We can measure the strong bands pretty well. The weak bands are very difficult to measure with a long path length at cold temperatures here on Earth. And that's actually important for other planetary studies for the outer solar system. So that direct solar beam measurement is really important to help us to interpret other data that we get back. The solar Oriole cameras are two polarization states, vertical and horizontal, and two wavelengths. There's one in the blue and one in the red. And we take an image very near the sun, about 6 degrees off the sun. As I mentioned last time, we're measuring the roll-off of the energy away from the solar disk. That tells you how many monomers are in each aerosol particle. And then we want to measure the phase function at 180 degrees from the sun. And that helps us, that determines the polarization of the light as it bounces off those aerosol particles. And that constrains the monomer size. After we have that, We can then use the up and down looking spectra as you descend through the atmosphere. You have the upward looking energy and the downward looking energy. You can subtract as you go down through the atmosphere, and you can get your down flux, your up flux, your net flux versus altitude, and that gives you your solar heating rates and your thermal balance. So it was a very well considered, well thought out instrument. The details of it were in last time's talk. So we launched in October of '97 on a Titan Centaur. We arrived at Saturn in July 2004 after a 7-year cruise. During that 7 years, we turned on about every 6 months, did an aliveness check, turned on our calibration source, which was a 3 incandescent lamp system with fiber optics that fed this very start of each optical chain. As I mentioned before, all of those measurements that we're taking from 6 spectrometers, 3 imagers, 4 polarizing cameras, all of those are interconnected. We needed to calibrate them with a single input source, and that's how we did that. We were rock stable over the cruise too, I just wanted to mention. Probe was ejected 17 years ago on Christmas Day, December 25th, 2004, and the Titan encounter was right at 17 years ago, January 14th, 2005. I wanted to mention that after we launched, we had several gravity assists to get us all the way out to Saturn. We did not launch and go to outside of our Earth orbit. We actually went towards the sun. We swung by Venus twice, swung by Earth, and then out by Jupiter to finally get to Saturn. My current program and other programs, I hear us talking about launch dates and how important it is to hold launch dates, and it is important in its own right. But when you're talking about planetary alignment for gravity assist, now that is a launch date you don't want to miss. So once we got to Saturn, Cassini dropped us. They did not propel us, send us, or thrust us. They dropped us. There was no thrusters, no propulsion on the probe. It free fell for 22 days to hit Titan. Goes through an aerobraking maneuver with the aerobraking shell, then drops the shell, deploys a parachute. We descend through the atmosphere on the parachute, drop that parachute and get a smaller one, and then have a surface impact. The total mission of the Huygens probe was 2.5 hours. To talk for just a second about how the data gets sent back to Earth, the DISR sends the data to the probe, which is just that disk. And then the probe sends the data to Cassini. Cassini reoriented and put its large antenna focused towards the probe. So we sent the probe sent the data to Cassini for storage and replay. After the mission was completely done, the data was then transmitted. Cassini reoriented towards the Earth. It was transmitted to the Deep Space Network, then to JPL, and then to the Huygens Probe Operations Center in Darmstadt. At the time, DISR's 15 megabytes of data seemed like an awful lot after you decompressed it. If you recall, we used RICE lossless data compression on a specially crafted hardware board developed by the Institute of Braunschweig. And after you decompress that data, it was 400 meg of raw data sets is what we were expecting. At the time, that seemed like an awful lot of data. Now it's somewhat amusing, I'll just say, but this was the days of dial-up modems, and we're just not at the place where we are now in 2022. The biggest concerns prior to the mission, I just wanted to set this up because we're going to start talking about how the mission actually occurred in the next slide. But we were concerned about the probe system success. You may recall that we found an issue with the communication link. I have a slide on the next page about this. The Doppler effect was omitted in the design between the transmitter and the receiver. It was just an honest omission. It's well documented in literature. You can see an IEEE spectrum from October 2004 to read a good article on it. There were two fixes. One was to slightly change the mission date so that the geometry between the Cassini orbiter and the probe was different and didn't have as high of a crosstrack there to give you the Doppler effect. Also, we had a known clock drift in the oscillator that drove the transmitter signal. And so we wanted to heat it. We knew that it would change with temperature, so we heated the whole probe. We traded our battery margin for that heating. And that was how we fixed that issue. And that was all figured out during cruise. We were also concerned that the probe may not spin adequately for the sun sensor to lock up. As I've mentioned, we had a lot of time and space dependent measurements, and we needed that sun sensor to lock up to tell us where the sun was, how fast we were rotating, and what azimuth we should take each measurement. It was all done not with artificial intelligence, because we did not have time to learn anything once we got there with a 2.5-year mission, but the software was a highly adaptive, very complex interrupt-driven software system, and based on the input from the sun sensor, it would determine where to take the measurements. We were concerned we might lose tiles after a 7-year cruise, and the aerobrake would fail and we would burn in the atmosphere. We were concerned about parachute deployments. We were also concerned about contamination going on the DISR windows, because that would alter our spectral transmission, and it would really impact our science. And then I will mention we were concerned a little bit about the thermal performance of DISR. The CCD had a cold strap that was directly connected to the outside surface of the probe. The temperature of Titan's atmosphere gets as low as 77 Kelvin, and the surface is at 93 Kelvin. That's pretty cold. It's out at 10 AU. And glass, and I might get the temperature wrong on this, I just can't remember, but seemed like the glass goes through a phase state transition at about 162 Kelvin, if I remember correctly. And the fiber conduit, as we talked about last time, is very closely mated to that CCD, only a few microns separation. And so we were concerned with the CCD being that cold, that the glass would also get too cold and go through its phase change and crack, and we'd lose the fiber conduit. And then lastly, we were pretty worried about those fragile fiber bundles, as we talked about a good bit last time. Okay, so how did the mission occur? First, the Comlink receiver command on the Cassini orbiter was not given to channel A. So let me explain how this works. The probe sends its signal to Cassini. It has 2 channels. The Europeans are really big on redundancy. So it has 2 links. Each of those links have 2 commands. You enable them and then you turn them on. Everything worked great except for the turn on command was not given to channel A. Now, we knew the basic design of the COM from very early in the DISR program, and we had to make a decision, and the decision is, do we transmit all of our data redundantly over both links, or do we hope that everything's going to work out great and get the added benefit of twice as many images? And so we made that decision. We designed in that software a lot of decision trees that watch the buffers as the telemetry buffers are being drained. We could accommodate if we knew that only one link was not working, we would change our whole data collection strategy. But we had no indication during descent that that receiver was not functional. And so this case was sort of non-optimal. It was like as non-optimal as you can get from a DISR standpoint. So we did lose half the images, and we lost a little bit of the spectral data at the very end near the surface. Mission as it occurred, number 2, spin direction. So the design was counterclockwise as viewed from above. As you can surmise from my refreshing of your memory on our different measurements, we had that solar Oriole that's got to be right off the solar disk, which means you need a baffle to keep the solar disk, the direct solar beam, off of your polarimeter field of view. And so we had a baffle for the solar Oriole. We had baffles for the upward looking spectrometers that would also take diffuse and direct beam data. All that baffling, data collection, timing, strategy, all of that was designed for counterclockwise as viewed from above. However, about 10 minutes into the mission, the probe reversed spin direction, and it continued spinning in the wrong direction throughout the descent. Now, recent wind tunnel tests done, I believe these were done over in Europe, they indicate that this is actually the expected behavior. If we had done those wind tunnel tests prior to launch of Cassini-Huygens, we would have known of this issue, but we didn't. And there's some pretty complex aerodynamic analyses that do indicate that this is expected. And there you have it. So that this is one of the areas, like the slide shows, 2019, I think, was when that was published. The impact on DISR was huge. We spun from the wrong direction. So all of that careful planning and the strategies for data collection, it was kind of a bummer, but there was grace. That has to do with the probe stability. The probe didn't just smoothly and calmly enter the atmosphere and just smoothly and calmly get down to the surface. There were a lot of high-speed gusts and tips at the higher altitude. It was really unstable. There was really a near call there. There was a large gust, and I'm not sure if it was this one or not, but we did hit a gust as high as about 270 miles an hour winds within seconds of that spin reversal. So if we had not been spinning and we hit that gust, boy, it would have been really touch and go whether it might have tumbled us. So we're very grateful that it didn't do that. We did have plenty of tips over 10 degrees at high altitude. Once you get down into the surface, the wind settles down. We'll talk about that more in a few minutes. Nominals around 3 degrees, and we were pretty stable down at the lower altitudes. In addition to that, even though we heated the probe before we got to Titan, it was very cold. That thermal strap that connected our focal plane to the outer area of the probe was very effective. Our optical bench got very cold. The sun sensor had a silicon detector. It operated, if I remember correctly, it's 935 nanometers. As that detector got colder and colder, the long wave responsivity decreases. It moves in as temperature decreases. And so the sun sensor was less responsive than we expected it to be. And so the gusts and the temperature caused the sun sensor to remain unlocked for most of the mission. So the bottom line is the impact on DISR is that we basically took random measurements as we went through the descent. And I'll just say thousands, millions of things occurred exactly as we designed them and as we planned them. The surface lamp worked. And I put in parentheses temperature because I wanted to remember to tell you the story. I mentioned the concern about the glass cracking when the CCD got really cold. Well, in Darmstadt, when the mission was occurring, you don't get any information because the Cassini is looking at the probe, not looking at Earth. When it played back the data, to Earth, it first just gave the engineering data. So all you get is temperatures and voltages. You don't get any of the science data. So we were huddled around these monitors, just a few monitors that had the displays of this housekeeping data. And of course, the optical bench temperature, the CCD temperature, I had all of those up. And was watching them, and we were cold. I knew we were cold when we went in, and it was cold, cold. And I just watched that temperature get closer and closer to that 162. My blood pressure was going up higher and higher. And then right when we were almost at 162, the surface science lamp turned on, and we got 20 watts pumping through the whole system. Oh, it was just wonderful. And so that was a great relief. So it did save our surface work, as well as giving us the good spectra down near the surface. We did survive landing. We operated for hours. We were still operating when Cassini went over the horizon. So all of that went well. And in the end, as we'll see, we accomplished this Huygens science goals. Honestly, Marty, Dr. Martin Tomasco was the principal investigator. He's the spiritual leader of the mission. Marty and I talked about a day and a half after the mission, after looking at this random data. We had both prepared ourselves for a mission that was a complete success, or for a mission that was a complete failure. Neither one of us were very prepared for what we got, which was random measurements, a lot of tipping and tilting, not knowing where the probe was, how it was oriented. And, I looked at Marty and I said, now we're going to find out how smart we really are. And honestly, we owe a lot to Eric Karkushka, who I gave credit at the beginning of the talk in the disclaimer slide. Eric really was able to piece together an awful lot about where the probe, how the probe was oriented and where it was looking throughout the descent. So kudos to him. So let's talk about some scientific results. That's how the Huygens mission occurred. Let's talk about the science. So basics, this aerosol haze, these tholins, extend from the top of the atmosphere all the way to the bottom. We really thought we might be able to have a clear view from 150 kilometers, but no, it extends all the way to the very bottom. Once you get to the bottom of the atmosphere near the surface at impact looks an awful lot like the Mediterranean coast, which was kind of fun since we had a lot of meetings there in the Mediterranean area with the European Space Agency. So that was kind of fun for me. We saw hills with riverbeds draining into a lake. You could see that hydrocarbons would be washed off these mountains into channels and then into a lake bed. I do need to say there was no liquid where we landed, but you could imagine that this is what you were viewing, and we'll see that together in just a minute. We determined a lot of atmospheric properties. We characterized the tholins, and just many of the goals were achieved, even with these random measurements. I did want to mention, you can see this tiny little writing here. There's, of course, way more science that we've discovered on Titan than can be adequately communicated in an hour. So on several of the slides, I have references to other papers. If you want to have more information, you can just screenshot those and read to your heart's content. Okay, now we're going to attempt to, let's see, I'm going to pause sharing. We are now attempting to show you a video. And can you confirm that you can see that video?
No,
we cannot.
Okie doke. I didn't quite do it right, so hang with me. I will. And I think now, can you see it now?
No.
Not yet.
Wow.
You can go back and go to the original plan, which was to share your desktop.
Yeah, I am.
Yeah.
I am sharing my desktop. Let me stop sharing altogether.
Yeah.
And now I'm going to share screen again and see if we can't do that.
We see you.
Hi.
Hi.
I think this is going to work.
Oh, looking better.
Is that looking better?
No,
It says you started screen sharing, so.
Are we there?
You have more than one
No.
screen?
no. No, we can't see the share.
Laura, do you have more than one monitor on your computer?
I don't. I'm going to try this one more time. Do you have it now?
Oh,
No.
no.
It doesn't like it when I go to full screen for the video, so I'm sorry about this.
Are you done with the PowerPoint?
I'm not.
Okay.
Make the browser that has a YouTube video in a bit smaller and share just that.
I did just now. Do you see it?
Not yet.
Oh,
It shows it's even highlighted. The green is highlighted. It's highlighted in green as sharing.
It may get there. It may just take a while.
That's unfortunate.
You had it working earlier, so what?
It's coming from Titan, so it might take a little while.
It might take a little while. It takes about 12 minutes, 10 or 12 minutes, if I remember correctly. So let me try this.
I think you should try again, just taking
Oh,
it into YouTube.
yeah, did you- Have you clicked on it? Or is it playing on your desktop?
It's not, it's just, I was just gonna share Google Chrome. I mean, I can,
February 14th,
Can you see
2005
it?
begins with the Earth passing directly in between.
Hear it.
can
We hear it.
you can hear it. Yeah. That's unfortunate.
Unscreen, get out of screen sharing.
Is it a YouTube video?
It is.
Do you want to send me the URL and I can see if I can share it?
Sure, it says it's sharing. It's green. It's showing shared. So that's unfortunate. So I'm going to stop sharing and pull up. Here's the URL.
Can you put it in the chat?
Yeah, I'm going to do that right now. There you go.
You want to try it? Peter?
Yep. Getting there, just getting past the ad.
I had to update the operating system on this computer, and that's what I think is the problem, is that it's not compatible with the Zoom that was running.
Here.
Okay, great.
Is that there?
Yes, that's good.
There.
Yes.
Yeah.
With the Earth
Can you
passing directly
hit
in
the full
between
screen,
the Sun and
Peter?
Saturn, an opposition so perfect that it occurs maybe thuyce per millennium.
No.
Meanwhile,
Okay, hold on.
Huygens probe quiet
Click to the right.
is about
All the
to
way
end its
there.
7-year journey. As Huygens approaches, the inner planets cluster around the distant sun. Saturn appears almost as
Can you
large
make it
as
louder?
Orion. A few moons are visible as white dots aligned with Saturn's rings, while Titan, its largest moon, is already well resolved. Huygens is destined for Titan, a mysterious world larger than the planet Mercury and shrouded by a thick brownish-orange atmosphere. The details of its surface have never been seen. Huygens' speed increases to near 6 kilometers per second, and Titan's disk quickly obscures our view of Saturn and its more intimate moons. As the probe enters Titan's atmosphere, the heat shield reduces the speed some 15-fold within a few minutes. The main parachute reduces the speed further. 15 minutes later, the smaller stabilizer chute allows a faster descent at first, but slows as Huygens enters the lower, denser parts of Titan's atmosphere. Huygens is approaching a dark valley between brighter, hilly regions. Beyond the hills to the left, two dark parallel lines appear, which are later discovered to be part of a vast system of dunes which surrounds the moon. At 21 kilometers altitude, the probe moves through a thin haze layer as seen on the horizon. The bright area near the center top is the glow of Titan's haze illuminated by the sun. A complicated system of drainage channels, some hundreds of meters wide and kilometers long, are seen cut into the hillside. These are probably the result of runoff from methane rain. Stereographic imagery reveals hills to the left to be perhaps a few hundred meters tall, while features in the valley are tens of meters in height. For most of the descent, the probe travels eastward above Titan's surface. However, below 7 kilometers altitude, the motion reverses into a backward westward motion. It reverses again at 1 kilometer altitude, and we move slowly southeastward. Hang on as Huygens lands on Titan's surface near a water-ice outcropping ridge. Another westward-looking view of the descent from 31 kilometers shows the area of Titan over which the probe has just flown. This affords us a good view of the drainage channels and apparent shoreline. More dark lowlands appear and a rough pitted hillside to the left. Spectra of the surface suggest that the bright areas are water ice, and the darker areas are a type of hydrocarbon mixture that has never been produced in the laboratory. The small white dot in the lower center part of scene tracks our progress over Titan's surface. We see the reversal in direction at 7 kilometers altitude, and we fly over the ridge near where we will land. As we approach the surface, our perspective brings the topography to life. We see that although there are rivers and a shoreline, the basin is dry. Below, there are distinct signs of erosion which crafted the rugged ridgeline. Huygens sinks into one of these gullies. We experience a relatively soft landing on Titan's surface. The view from the surface reveals an amazingly Earth-like picture of a dry riverbed, with distant hills which are a few meters in height. Some seconds after impact, the shadow of Huygens' parachute drifts across the scene. The heat from the surface science lamp in the probe's skin vaporizes methane from Titan's surface, which is about 180 centigrade degrees below freezing. Near the probe, the ground is littered with water ice rocks and smaller pebbles which could be made of water ice, or hydrocarbons, or some combination thereof. Although we now know more than ever about this mysterious world, many questions remain unanswered. Where is the vast reservoir of liquid methane necessary to replenish the atmosphere? Where and how often does it rain on Titan? How does the methane get recirculated into the atmosphere? What materials make up the surface? What processes create and shape the hills, dunes, and valleys?
Okay, thank you, Peter, for showing that. And just to highlight that latter part where you see the bounce and the wobble and all of that, that is taken, we took many, many images of the surface of Titan after landing, and you can see small variations in those images and back out what the probe activity was. So it's not like we were imaging that fast. We didn't have that fast of a frame rate. That was sort of interpolated. Peter, if you would, I have another YouTube link that I placed in the chat. If you could share that video also. And what I'd like you to do is to share that for about maybe 15 seconds and then pause it. I'd like to orient us to what we're actually seeing. And then I want us to listen to the sound of Titan Microphones were flown on the probe so we can get the sound of the winds during the Titan descent. And I'd like to do that while we're watching that, a portion of that video. We're not going to watch that one in its entirety. Right. Okay, so just pause it there. Just pause it there is great. Okay. And could you maybe remove the gray screen on the right-hand side? Perfect. Perfect. Okay. So this is something that I wanted to share with you. I've sort of brought you into the DISR world, the engineering world, the behind the scenes tour of Titan. And this video would be of more interest from that perspective. Up in the upper left side, you see an image of a height of a person. You see the probe under the parachute, and you'll see it rotating and tilting and tipping as it actually did on Titan. Below it, the green line is the lat lawn. It's how it was moving over the surface of Titan. At the bottom on the left side, you see Titan. You see a scale height of Mount Everest to get a relative perspective of where we are coming down onto the surface. And then where Cassini is, the sun and east. So that's what's going on at that far left side. The large circle, of course, is the measurements themselves. Because these measurements came in randomly, you will see them coming in randomly. You'll see how we have to piece together the information that we receive to give you that video, that nice, smooth, clear video that you saw before. On the right-hand side are all the basic standard kind of logistical things about the mission. So your altitude, your speed, your temperatures. The images are all color-coded. You can see those as they come in. The spectra are also color-coded. The single detector readings are also, and then the signal strength is down there towards the bottom, signal strength to Cassini, and then you've got your rotation. So to me, the sound effects, the sounds all relate to the signal strength and to the spin rate and to the images, each of the measurements that are being taken. To me, it's somewhat irritating. So what I'd like to do is, Peter, if you would turn your sound off and then move the viewing instead of 44 seconds, move it to where we can start to see the surface. It's around, yeah, around in there is good. Yeah, somewhere in there. And I am going to play the sound of Titan as Peter plays the video. So we'll do this for, I don't know, let's say a minute. Let's go for about a minute. Okay.
Laura, we don't hear the sound.
You don't hear the sound at all?
Oh, no.
No.
Well, I'm playing it as loud as I can. Maybe I'll try to play it on my phone. I don't know why you can't hear it.
Play it separately after this video for a few seconds.
Yeah, okay. We'll do it at that point. Okay, it's about this point that the wind changes and we start drifting. You can see the two dots on the surface below us. One is Nadir and one is the landing site. And we're starting to go towards the landing site now. Okay, Peter, I think that's it for that video, but you've got the link, everybody, if you want to watch the full thing. It's kind of interesting from an engineering standpoint, now that you guys know, more about the mission itself. So I will attempt again to share my screen with just my regular PowerPoint. And not working as well as it could. Can you see that?
Yes.
All right. Now, browse.
See that one?
There it is. Got it. I am trainable. Okay, so I'm going to put this on the screen.
She is not trainable.
I am trainable, but just barely. So you guys screenshot that, because I'm a little bit disappointed it didn't work as well as I wanted. And so anyways, there's the good videos. And I guess we didn't hear the audio. I heard it fine, but you guys didn't hear it. So let me play some audio here for you. Can you hear that?
Nope.
It was just a second.
Can you hear that?
Yes. No.
Yes. So turn up your volume. It's going to sound like static. It's wind. That is the wind at Titan. It's very windy.
Yep.
It sounds
It only
like
plays for a second. It appears Zoom is doing some kind of signal processing to remove noise from your computer.
Can you guys hear this?
Yeah, I think if the rest of us mute, maybe I think our sound is overtaking your sound.
Okay, yeah, if you would go on mute, and it's going to sound like static. You're going to think, and in fact, your computers may even, do a noise canceling situation. So mute yourselves. I'm going to play it. It's pretty loud in this room, so hopefully you can hear it. Let me know if you can't.
We hear it for exactly 1 second at a time, and then it shuts off.
You hear, well, it's pulsing because we're spinning, we're moving. So
okay,
we're going under the probe and we're tipping. And so you're going to hear pulsing, because that's what Titan sounds like if you're on a parachute tipping.
Right, Laura. I'm used to this audio. We're not hearing it. And others think Zoom is like canceling it out because it's mostly static. Well, we're not hearing the right audio.
Well, that's also unfortunate. I hear it very loudly. It's full volume.
You have to play it on a different device to the one that's doing the Zoom. Otherwise, the anti-feedback will take it out. Or you have to do it with screen sharing of the thing that you're playing.
Okay. I think that's going to ask a little bit too much during this.
If you want to send me this slide, and I can forward it to everybody, Laura.
Okay.
And people can listen to it.
Okay. Great. I will give you the whole presentation. Be glad to give you the whole presentation. So yeah, this was a kind of an innovation in the aerospace industry. Someone at the European Space Agency had the idea of putting a microphone on the top of the probe. And so they recorded the audio of the descent, and that is now included in a lot of missions. So it's a really cool thing. I like, as I described, I really like to play it over the engineering YouTube. That the engineering YouTube's audio is really irritating to me, and so it's nice to see it. And I do encourage you to watch those and listen on your own time. It's pretty amazing just what you're seeing when you go into the Titan's atmosphere, what you're hearing, and then also as you see the information that we received back relative to what we had designed DISR to provide us. It's really amazing that we got back as much as we did. And a lot of kudos go to Eric, to Marty and Lynn, to Chuck C, and to the whole team trying to patch things together. So let's move on. Let's talk about some of the more academic aspects of Titan. So the haze particles go all the way down to the surface. We had hoped we would see the surface at about 150 kilometers. We were able to see the surface right around 50 kilometers. We did drift over that bright dark boundary, which was a real plus. We didn't know if we were going to be able to hit that or not, but that gave us a feel for what we're looking at. When we're looking at from Earth, you can pick up bright and dark boundaries, as we saw last December. And so we got to see both of them in that 2.5-hour descent. It was great. Our resolution varied from about 80 meters to better than 1 meter, of course, when we're sitting on the surface. Those rocks that you see on the surface, they're about 3 inches in diameter or something like that. So this is, just one view. We're seeing those bright highlands. It looks like we've got rain-fed streams into this dark, dry lake bed. As the video mentions, these dark areas we think are water ice. Water behaves on Titan kind of like rocks, like silica does on Earth. So water is like our rocks out at Titan at 10 AU, and methane is like our water on Earth. And then, of course, the atmosphere has a lot of nitrogen in it. So it's a very Earth-like environment. We're going to zoom in and look further at this area. This area was imaged at several altitudes, so we were able to do some stereographic projection. I will mention these longer, straighter cuts. Those are indications of cryovolcanism. This is more indication of rain. It's methane rain. Washing those hydrocarbons off of those highland areas into streams, creek beds, and then down into the plain that we actually landed in. So as I said, we'll zoom in a little bit. These are very steep channels, very rugged channels. You can do the stereographic projection here and see this is really high. That's this area here, super high, and then super low down in these channels. This is still being studied now. I'll butcher her name, Chloe Daudin in Paris has improved on this analysis recently. It still is basically the same, but she's improved on it and come up with some more intuitive interpretations of some of the details in how the fluid, how that methane rain travels over this area. So this is a 3D model. Again, she has improved it, but this is the old one. If you take a cut from A to B, that's shown in the graph at the lower left from A to B. This is height in meters and then distance in meters. So A to B is kind of a good hike, a good brisk hike. C to D over this channel, you're pushing pretty hard, slopes about 30 degrees. So some pretty rugged terrain on the surface of Titan near where we landed. This shot I really like. This is, of course, the landing site. That the bright spot at the bottom is the surface science lamp. And then the moon with a similar scale or similar perspective is placed alongside. These rounded cobbles are water ice, like I said, around 3 inches in diameter, roughly. And because they're smooth like river rocks, it indicates that there's fluid flow. As I said before, we didn't land and see any fluid. There was no fluid at the site, but indications are from looking at it that there are times that fluid flows over that area. Now, so what is the surface reflection spectrum? We brought that lamp so that we could get some good surface spectra. The actual Titan surface is the black line. And do you see how nice and flat and regular it is? That is not expected. We would expect to see some of the more common hydrocarbons represented and see those hydrocarbon signatures, but we do not see that. We see a very flat IR decreasing spectra. This was not expected. This is not repeated anywhere that we know of in the solar system at this time. It is still an area of active research. There is some thought that perhaps the tholins themselves have this spectra, but how they would have it, we don't know. We did land, as I've said, it was not wet, there was no liquid, but it was a liquid saturated surface. It's like damp sand that we landed in. The surface science lamp heated up that damp sand, evaporated the methane. The GCMS measured that methane. And so we kind of know what we were landing in to some extent, but this surface reflection and the composition of the surface is still a real mystery. And there is more information available there in that article. So we got a bit on the nature of the surface and the topography and composition. We're going to talk about the wind direction. I pointed out in the video that at about 8 kilometers, you change direction of spin, and then you go over here and then land at the bottom. So at high altitude, the wind blows prograde, so it blows very fast in gusts in the direction that the planet rotates. We did suspect that before we got there, and that turned out to be correct. At high altitude, we had very high wind speeds. Those wind speeds dropped to 0 at about 80 kilometers, increased again, and then dropped to about 0 at the surface. And the direction of the wind changes in that last 8 kilometers. So we did learn a good bit about the wind direction, but we need the ground track to do that. And because we didn't see the surface until we were at about 50 kilometers, we only know high details about the wind under the 40 kilometers. Okay, let's talk about these aerosols. So the aerosols are modeled with a fractal aggregate model that was developed by Mark Lemon. This is what one could look like. This is about 2048 monomers with about 4 micron radius. And the scales on each side are in numbers of they're in monomer radius, if you will. A particle with, and keep this in your mind, a particle with 4,300 monomers would be similar, but still larger, more than twice as large. So kind of like a snowflake, kind of spread out, light and airy, not clumpy. So we were able to get a few of these solar Oriole measurements. We got, I think I remember like a dozen of these good solar Oriole measurements. This is one of the better ones. And if I want to highlight the black line, you can see with the black that there's actually 2 things being plotted on that picture. So this was work that I actually did. It's running radiative transfer models with variety of monomer size and particle size and getting and trying to match how that roll off of the Oriole comes off of the solar disk. And so I found that about 0.5 microns and then about 3,000 in each particle matched the signature that we saw. Some greater refinement. They did some polarization studies after I stopped working on the program and refined that to the radius is about 0.4 micron monomers and about 4,300 monomers in each of these particles. So these haze particles are very light and airy and fluffy. They're super fluffy, way more than we expected. We expected like 200, most of our models were run at 256 and we got 4,300. So very different than what we had expected. Light, fluffy aerosols from the top all the way to the bottom. They completely fill the atmosphere. There's dark, they're very dark up here at high altitude. As you get lower, around 80, they get brighter. And we think there's liquid ethane condensation onto these light, fluffy particles. And then down even lower, they get still brighter. We think maybe even liquid methane condensing. Now, the conditions would allow ice to form at these, so icy clouds. We didn't necessarily see evidence of that. We can't separate all the variables to know exactly what's happening, whether you're getting spherical particles with these liquid condensation or whether you're still getting these fluffy aerosol particles that are extending to the surface. We know we're getting them, but what the characteristic is down at the bottom, we're not quite as sure. So there's some interesting things about this Titan haze. So we took data from about 160 kilometers down. Images of Titan show that there's a detached haze. There's a ring of haze at super high altitudes. Then it's clear around 500 kilometers and then hazy again where DISR measured it. So the Cassini neutral mass spectrometer detected haze particles all the way up at 1,000 kilometers. So really high. What is going on? We know that UV light down at 160 nanometer, it dissociates methane. And that UV light gets down to about 500 kilometers. So we really thought that methane haze should start at about 500 kilometers if it's caused by the UV. Well, it starts at 1,000. So that's not the mechanism. As it turns out, a much shorter wavelength UV is interacting with that methane. It's not only dissociating in it, but it's ionizing it. So these ionizing reactions are making solids, and those solids are falling to about 500 kilometers, and they continue to get larger, coagulating more and more, making these light, fluffy particles. They're falling faster, and they make that clear space in the haze that we see. And the key result here is that the haze is produced by ionized chemistry, not neutral chemistry. And so this was unexpected, new information. A new theory of the Titan atmosphere supports it, and it actually predicts larger particles around the 0.4 to 0.5 micron with several thousand monomers. So ta-da, it looks like we're onto something there. That was a big success for learning more about Titan's aerosols. So let's talk about the methane mixing ratio at the surface. It's about 5%. And I'm going to go fast through these because I think we're running a little bit out of time. So we've got about a 5% mixing ratio near the surface. That results in about a 50% humidity. We'll see in just a minute. So this chart is about the methane absorption coefficients. You have to separate out your variables, your methane mixing ratio, your aerosol absorption properties, and your scattering. And so what you do is you use the lamp in the last few minutes, you got a short path, and then you trust the GCMS to measure your methane abundance at the higher altitudes. And when you do that, these are your methane absorption coefficients. On the left-hand side, this is what we had expected to see, but you can see the dots are very different from the lines. The dots are the measurements. And then on the right-hand side, we have new model with new absorption coefficients. And this is helpful, like I said, for many planetary studies, not just for Titan. And then we can use those new methane absorption coefficients to learn more about the atmosphere. So we've got about a 50% humidity there at the surface. So it is cold and humid at the surface of Titan. At about 40 to 80 kilometers, you're at 100% humidity. That was measured by GCMS. So like I mentioned, you could support liquid or ice clouds. We didn't see those in our descent, though we saw that very thin cloud layer at about 21 kilometers. But nevertheless, there's not enough condensation on these aerosols to clear them at any altitudes. So we did, because we've learned about the aerosols and about the methane coefficients, we can then do some heat balance, some solar heating and thermal cooling rates versus altitude. We did that. It shows that you heat faster than you cool over much of the altitude of the descent of DISR. So that means that energy transport has to be taken to other latitudes to move the winds around. And there's an article that you can read about that mentioned there in the side. So we were able to hit a lot of those science objectives, have many questions still. We want to know more about the rain itself. What exactly is that flat black decreasing IR signature? Why does the wind die at 80 kilometers? How does the forcing dynamics work over the whole Titan system rather than just at our landing site? And what's going on more about the surface topography? And so as a result, Dragonfly has been approved. We're going back to Titan. It's a rotorcraft. It's made by Johns Hopkins APL. The plan is to launch it in 2027 and land in 2036. And there are some resources there to learn a little bit about Dragonfly. I personally am not working Dragonfly. I'm working JPSS, polar orbiting weather satellites, but Goddard is leading the effort there for Dragonfly. So I just want to thank you for the opportunity to share a little bit about DISR and Titan with you, and it's been a pleasure.
Thank you so much, Laura.
Thank you.
I guess we have a little time for a few questions. If somebody wants to ask a question of Laura, go ahead.
Mute.
I have a question for you. What is the pressure near the surface?
Oh, that's a logical question. Give me just a second. I don't know it off the top of my head, but I've got it right here. Hang with me. Surface. It looks like 10 to the third HPA. I was going to say, put it in bars. I don't remember Pascals, but I don't remember what the H is. Sorry.
I would guess it's close to the Earth because Titan's close to the Earth's size, but don't know that.
H of the hectare, that's 100 pascals.
Yeah, a thousand HPA is 14 PSI.
Right.
There you go.
Yeah.
Wow, that's really interesting.
Yeah, it's close to the Earth. Laura, when I worked on the proposal, I remember I had to do some radiometry on liquid lakes and oceans of methane. Can you comment on what do we find in lakes and seas of liquid methane?
Okay, so at the landing site, there's none. At the landing site, it was damp sand. It was definitely methane, among some other things, other constituents as well, but predominantly methane. But there are lakes at the pole of Titan. And so there's large liquid methane at the poles, and Cassini did more of that work. And so that's about as far as I should probably comment on it.
I have a question, Laura. This is Ripu. I can't do the translation very quickly, but it looks like it's about 1/10 of an atmosphere pressure, but it's also very, very cold. Those are the conditions that might, I think the methane clathrates that we talk about, that we are concerned about for greenhouse gas emissions, because these hydrates may be forming. And I don't know if you looked in the modeling for the infrared, whether the possibility of the clathrates formation and what that does to the spectrum.
Yeah, I do not know. I don't know, but I do know that we have been looking, and the science community has been looking at Titan because it's a natural greenhouse effect. You know, it's a early Earth frozen in time, and it's got that smog and, you know, all of those things. So people are looking at it in those terms, but I don't know if they've specifically looked at the clathrates.
Jump in because I have a question.
Yeah. I have a question.
You're the lead-in.
When the probe was going down through the atmosphere, you had no foresight as to what it was going to land on. In the picture you showed, you said, here's the landing site. Now that's something you knew afterwards.
Right.
Because so
I lost your audio, Dave.
Yeah, you muted somewhere.
no, we went to mute again. So the wind was blowing one way, then it was blowing the other way, and the probe was going with it. You could have wound up anywhere, on a mountainside, in a lake, and you didn't know that. And you pointed to the landing site and the point right under the probe, and they came together at the end, which is really good. But
Yeah, I
okay.
think that was that post hoc analysis there. That was landed.
Definitely post-processing, definitely. And you're right, we didn't know. And I think that that's is sort of part of the wonder of the whole thing, because we had to design the instrument to be adaptive to its environment, not knowing what we would see. And we were very fortunate to see both bright and dark, and to land in a place that was stable enough for us to settle and take additional measurements. It was really very opportune in many respects. Yes, Judy.
Okay. You did a lot of spectrometry, obviously. Did you find other things? For, you know, when we go out in space and measure that, very often we're finding amino acids that we don't expect, and many other minerals and other items that we know about here. And I just wondered if that was part of the study.
Well, lots of different hydrocarbons, you know, tons and tons of hydrocarbons. And there's some argon, you know, that you would expect. And they may have found more things. I'm not aware of them right now myself.
Thank you. It's very interesting.
Are there any follow-on missions planned?
Laura, can you comment on the topography a little more? What's the highest mountain and the lowest valley on Titan?
On Titan as a whole, or, you know, the landing site, so this was the, let me scroll back. So I think in that 200-meter range are the higher areas. And over the whole area, you know, because we didn't get multiple resolved images of recognizable features, you know, we don't have a large sample to get heights. I don't know what the orbiter studies have done. So the ISS, I guess, might have been able to get more. I don't know whether they got any. So if you want to talk about all of Titan, that's a Cassini problem, not a Titan problem. But as far as the Huygens site, I think in the couple 100 meters is as high as it gets. Are there any other questions? And I think, Peter, you asked about follow-on missions. And the Dragonfly mission is, I think, considered a follow-on mission. It's different. And they are interested, they're marketing it as a search for life type mission. There's a lot on Titan that reminds us of Earth. And so that's how they're marketing it. I'm not sure haven't gone into the detail on all the instruments that they're bringing with them and whether they're going to get some additional good information on surface composition. I would bet they do. They're going to land. It's a rotorcraft. They land and then they move a little short way away and then they land again. So I would expect they'll do some good surface composition work there.
Laura, I have one question for you. This is Dan. On your last presentation, if I remember right, you didn't expect the instrument package to land. You kind of talked about it as it was going to descend and it was a 2.5-hour mission. I was happy to see that it landed and got some pictures. Was the 2.5-hour mission based on the window at which it could send data to the Cassini? Is that what that was? Because I got the idea that it was never going to land, and I was happy to see pictures from the surface.
Oh yeah, I didn't mean to miscommunicate that. We did hope to land. There was a surface science package whose whole function was to take data at the landing. It was outfitted with a prism and a light source so that if we landed in liquid, it could shoot light through that prism and do spectroscopy of the liquid that we landed in. As it turns out, we landed on, damp sand. So it had a little
bit of vapor or something from that.
It had a little, it was a pressure sensor that as it landed, it could tell the pressure, what we were landing. And and so we did expect to land. The 2.5-hour mission was 2 hours of the descent, which, it's going to be an estimate. We didn't really know. It depended on what the wind speeds were and how the probe actually behaved in the atmosphere. So it was a 2-hour descent and then a half-hour on the surface was what we planned for. We actually were on the surface much longer. I mean, we took data on the surface for much longer. The 2.5 hours was, I think, a sizing for the battery life. Once you're on the surface, you only But we lasted much longer. So we were still sending data out when Cassini went over the horizon.
Okay, and then on the Dragonfly, as a biochemist, I don't know of anything that lives or any metabolic processes that can occur at minus 160 centigrade. It would be interesting to see. And the other question would be is how long are you going to measure it for? Because if you had something at minus 160, it probably wouldn't grow and divide for 10,000 years. So,
yeah, I think they're thinking, when the sun goes red giant or something, Titan will become much more like Earth. It's got lots of water. It's, anyways, it's not in my lifetime.
Okay, all right. Just pushing for this interplanet, this life outside Earth has kind of become a big thing, but at minus 160, even if it's there, it's frozen. It's gonna be.
Oh, it's very frozen. We call it the Titanians. The Titanians are very, very frozen for sure.
Okay. All right. They won't be attacking quickly. If they attack the Dragonfly, it won't be very quick.
Those rocks that were in the foreground, correct me if I'm wrong, Laura, those are ice that are covered to look like rust with dust. And they've been ice for billions of years. When the sun becomes a red giant, they're going to melt.
That's right.
Be water on Titan.
That's right. That's absolutely right. In fact, it's not just the rocks. Those rocks are water ice. All of that is water ice. All the bright areas are water ice. And then we have the hydrocarbons down in the surface. Titan is just so intriguing because it is very much like Earth. It's just at 10 AU. And so its processes are different. But it's very, very much like Earth. It's really a beautiful and intriguing place. And I'm grateful for the opportunity to talk to you about it. I'm sorry that the technical difficulties, we can get to Titan, but we can't run Zoom and YouTube at the same time. Some things are too hard, and I will accept my limitations and accept defeat in that area. But really, you know, I encourage you, if you're interested in further study, there's a lot published and a lot of it is in open literature. There's really an awful lot of work that continues to be done on the data that we sent back. It wasn't that much in terms of number of bits, but there's a lot of content there, and people are smart enough, people smarter than me are smart enough to pull out an awful lot of science about Titan from the mission.
Okay, Laura, well, thank you so much for 2 wonderful talks. And let's all give her a hand. And the first Wednesday in January, tune back in at 6:30 Pacific. Thank you, Laura.
Thank you, everyone. I really appreciate the opportunity to share.